Hello my friends and welcome back to the You Can Do TV channel.
Steel wire rope production kicks off with high-strength wires drawn and twisted into powerful strands. Automated machines braid multiple strands together, building up ropes designed for heavy lifting and demanding tasks. Each rope is measured, cut, and tested for both strength and flexibility. It's remarkable to witness this much steel transformed into reliable cables, ready for construction, industry, or anywhere brute strength and safety matter most.
Steel lifting slings are crucial tools in heavy lifting applications due to their strength, durability, and ability to handle extreme loads. These slings are used in industries like construction, shipping, and manufacturing, where lifting heavy loads safely and efficiently is essential. Made from high-strength steel wire ropes or chains, steel slings come in various configurations depending on the weight, shape, and type of material being lifted. Wire rope slings are composed of multiple strands of steel wire, typically arranged in a spiral configuration for flexibility and strength. They are available in different diameters, ranging from 1/4 inch, 6.35 millimeters, to over 3 inches, 76.2 millimeters, with breaking strengths varying accordingly. For instance, a 1 inch, 25.4 millimeters diameter wire rope sling can have a breaking strength of approximately 87,000 pounds, 39,460 kilograms. These slings are commonly used in lifting steel beams, machinery, and other bulky materials. Chain slings, on the other hand, are made from alloy steel chains that offer exceptional durability and resistance to abrasion. They come in grades such as grade 80 or grade 100, which are engineered for heavy-duty lifting applications. A grade 100, 1/2 inch, 12.7 millimeters, chain sling has a working load limit of around 15,000 pounds, 6,800 kilograms, while a 5/8 inch, 15.88 millimeters, chain can handle up to 22,600 pounds, 10,251 kilograms. Chain slings are preferred in harsh environments, such as construction sites, because they resist damage from rough handling and can be repaired by replacing damaged links. Steel lifting slings also come in multi-leg configurations, 2, 3, or 4 legs, for balancing loads. For example, a 4-leg wire rope sling with a 1 inch diameter and a 45-degree angle can safely lift up to 120,000 pounds, 54,430 kilograms, making it suitable for transporting massive structures like steel frames or ship components. Making a 4-strand rope of tarred hemp for historic ships like the Garine requires not just skill but also access to a well-equipped rope walk. In Alvangan, Sweden, ropemaker Sarah and her apprentice Niklas, along with Bernd from the Ropemaker Museum, worked together to craft such a rope using a full-length rope walk. This is a significant step up from the shorter rope walk they have back home in Hardanger, Norway. The Alvangan rope walk allows for the production of longer and thicker ropes, essential for rigging on historic ships. The Garine, a Galeas ship from Hardanger, is being restored with traditional methods and materials, ensuring that it stays true to its historical roots. The use of tarred hemp is especially important as it replicates the original materials used in ship rigging centuries ago. Tarred hemp, a natural fiber treated with pine tar, was commonly used in traditional rope making for its durability and resistance to rot. This treatment not only protects the rope from the harsh marine environment but also gives it a characteristic dark color and a distinct smell. The process of making the rope begins with preparing the hemp yarns, which are evenly spread and coated in tar. These yarns are then twisted together to form strands, which are further twisted to create the final rope. The full-length rope walk at Alvangan is equipped with advanced technology for driving out the rope, ensuring consistency and strength along its entire length. This technology allows for the creation of much longer and thicker ropes than those that can be produced on the 80-meter rope walk back in Hardanger. The rope walk in Alvangan, with its extended length and specialized machinery, can accommodate large-scale projects like rigging ropes for the Gareen. As Sarah and Niklas worked under the guidance of Bernd, they meticulously spun the 4 strands of tarred hemp into a single cohesive rope. The 4-strand construction is crucial for ship rigging, as it provides the necessary strength and flexibility required to withstand the stresses of sailing. Each twist and turn in the rope-making process is carefully monitored to ensure that the final product meets the high standards needed for maritime use. This project exemplifies the traditional craftsmanship that is still alive today, passed down through generations of rope makers. By using historic techniques and materials, Sarah, Niklas, and Bernd are preserving an important aspect of maritime heritage. The Gareen, once fitted with this rope, will sail with a piece of history woven into its rigging, a testament to the dedication of these artisans. Textile webbing slings are made from high-strength synthetic fibers like polyester or nylon. The process begins with weaving yarns into a flat, flexible webbing using specialized looms. This webbing is then cut to the desired length and reinforced by sewing multiple layers together for increased strength. Next, loops or eyes are sewn at both ends for attachment points, reinforced with additional stitching for durability. These slings are often dyed or labeled with safety information, such as load capacity. Finally, they undergo quality inspections and strength testing to ensure they meet safety standards. Textile webbing slings are lightweight, flexible, and designed to lift heavy loads without damaging the surface of the items being lifted. Recycling fiber ropes offers a significant opportunity for companies to boost sustainability while reducing costs. Worn-out and rejected fiber ropes often pose a disposal challenge, as incineration and removal are energy-intensive and lead to higher CO2 emissions. However, these ropes can be recycled into raw materials for new products, offering both environmental and financial benefits. By recycling end-of-life fiber ropes, companies can turn disposal expenses into opportunities for creating value. This sustainable process reduces dependency on imports, as the raw materials are produced locally, providing greater control over resources. Incorporating recycling practices for fiber ropes not only helps reduce environmental impact but also generates significant savings. By embracing sustainability, your company can benefit from cost-effective, eco-friendly solutions that enhance both profitability and resource management.
Here's how industrial-strength roller bearings are built to handle extreme loads. It starts with forged steel rings, turned, milled, and heat-treated for strength. Grooves are ground with extreme accuracy. Rollers and cages are assembled by hand, ensuring perfect spacing and motion. Each finished bearing is inspected and tested, ready to support tons of rotating force. Every detail matters when building something this advanced. Assembly of the F6000 begins with a high-stability cast base, machined to ultra-tight tolerances. Linear guides, dual-drive ball screws, and bearing blocks are installed for rock-solid motion. The spindle unit and rotary axes, developed in-house, are fitted with thorough alignment. Technicians route complex pneumatics and wiring to form the machine's nervous system. Finally, a round of calibration and diagnostics ensures 5-axis performance is razor-sharp. This isn't just assembly, it's crafting the heart of modern manufacturing. Watch flat steel sheets become fully functional tanks. First, CNC plasma cutters carve plates into custom profiles. Steel plates are rolled into curved shells, then tack welded into shape. Pipe sections are joined next, multiple cylinders aligned and welded to form the full tank body. A robotic arm ensures strong, even seams throughout. Nozzles and fittings are added, followed by the domed end caps. From loose parts to a sealed vessel, every weld counts. It's satisfying to see raw steel shaped into something this functional, with strength built in from every step. From massive forgings to ultra-precise bearings, the process is intense. Steel billets are first sawn, then heated and pressed with a 1,600-ton hydraulic forge. Each ring is rolled on a 2.5-meter CNC machine and tempered for strength. Rough and finish turning follow, along with raceway cutting and grinding. CNC accuracy hits 0.03 millimeters. Internal and external gear teeth are machined within 2,000 to 5,000 millimeters diameters. Final coatings like blackening or tempering are applied on demand. Seeing raw steel evolve into high-performance slewing bearings, engineered to handle load, rotation, and time, is nothing short of impressive. Structural steel doesn't shape itself. Here, 3D models guide every beam through CNC drilling, robotic coping, and tab welding. Precision built for field installation. Each step is verified before final coating. From raw profiles to job-ready components. Structural steel fabrication like this shows how digital planning becomes real-world strength. That's satisfying to watch. Casting a sandwich panel takes more than pouring concrete. It's all about precision and timing. First, the bottom and top shutters are positioned hydraulically. Reinforcement is placed on surface A, guided by window molds and side markings. Concrete is poured to a specific level. Metal pins bridge both layers, embedding into each side. Once surface A reaches 9 megapascals, the mold tilts horizontally. Shutters unlock, and the second pour completes the panel. Watching two concrete faces unite around insulation like this, so controlled, so efficient, it's just satisfying. Turning raw plate into a pressure vessel is no small feat. It starts with material storage and QA release. Massive 3,200 millimeters wide plates are blasted clean. Then cut using drill, mill, plasma, or oxyfuel. Rolled into perfect curvature, the shells take shape. Twin tandem sub-arc welders fuse the seams, followed by precise weld overlays. Robotic arms handle 3D cuts for nozzles, both on domed ends and cylindrical shells. GMAW robots seal it all together. Parts are heat-treated, primed, and ready. Watching this level of coordination, from blasting to robotic penetration cutting, is seriously impressive. Every weld, every curve, serves pressure, heat, and time. That's engineering at work. Watch straight pipe become precision curves. Hot induction coils heat the steel. Then controlled force bends it to spec. Simple in appearance. Surprisingly technical underneath. That's bending mastery. Here's how structural steel takes shape. Bold, heavy, and built to last. Plates are flame cut into custom profiles, then drilled and milled for connection points. Beams move through CNC lines for coping, punching, and slotting. Welders assemble frames, bracing them for strength. After inspection, surfaces are cleaned and coated for corrosion resistance. Behind every building is work like this, precise, rugged, and made to hold. Structural fabrication may look tough, but it's all about accuracy. Twin 9-kilometer tunnels. 5 new stations. Melbourne's underground is taking shape. Massive, complex, and transformative. Infrastructure like this doesn't just serve, it reshapes a city. Final assembly. Full-scale test. The Octocong vibratory hammer was fully assembled and tested on a full-scale pile before heading to China. Built for the Hong Kong-Zhuhai-Macau Bridge, it's not just heavy machinery, it's engineering built to shake the earth. From rod to ring, under 8,000 tons of pressure. Oil hydraulic presses shape metal into square or round forms while enhancing its structure. Heavy forging that's both forceful and precise, mesmerizing to watch. This is where massive marine engines take shape. Cylinder heads are machined. Rods bored and tested. Plasma tools carve valve profiles. In assembly halls, each component locks into place, backed by R&D and full load testing. From raw parts to ocean-ready power, it's precision manufacturing on a scale that moves ships. Shaping a differential gearbox housing isn't just about cutting metal, it's about total control. The PVSL 2-2-2 machine handles both turning and milling in one setup. From raw casting, the housing is clamped, then precisely machined, bearing seats, bolt holes, and sealing surfaces all cut in one pass. Live tooling rotates for multi-axis operations, while in-process measurement ensures tolerances are met. Fewer setups mean less error and tighter consistency. You can hear the efficiency, the seamless transition between spindle and turret. This isn't just a part, it's the heart of a drivetrain, and watching it come together like this, that's when machining becomes something more. Turning and mill turning redefined. This is solid cam in action, turning solid metal blanks into precise, complex parts. It starts with a rotating workpiece mounted on a lathe spindle. Cutting tools move in sync to remove material layer by layer, creating smooth surfaces, sharp contours, and perfect diameters. Next, the mill turn process adds another level of capability. Live tools rotate at high speed, enabling drilling, slotting, and contouring operations on the same machine without needing a separate setup. Toolpaths are programmed with SolidCam's iMachining technology, optimizing speeds and feeds to reduce cycle time and extend tool life. Watching the machine dance between axes with zero hesitation, it's oddly satisfying. Coolant systems keep temperatures down, chips are cleared efficiently, and tool changes happen in seconds. From aerospace to automotive, this is how high-performance components come to life, with speed, intelligence, and serious metal-cutting power. What does it take to make a professional-grade screwdriver from scratch? Let's follow the process from steel coil to package tool. First, high-grade S2 steel is straightened and shaped, flattened for slotted heads or precision cut for Phillips tips. A flange groove is machined on the opposite end to lock the blade into the handle. After that, heat treatment boosts strength, followed by sandblasting to prepare for plating. Next, plating is applied to protect against corrosion. The blade is then inserted into an injection mold, forming a durable ergonomic handle. Each tool is color-coded by drive type and torque-tested for reliability. Final touches include size printing and packaging. Every batch checked twice before shipping. This isn't just tool making. It's metal, molded with intent and tested for everyday performance. Curious how molten gold becomes wearable art? Let's follow the full journey, from a soft wax mold to intricate cast-ready tree forms. A soft sheet of orange wax is pressed over the model by hand, using a metal mold holder. This step captures every groove, curve, and fine detail without the need for heat. Once shaped, the wax form is removed, revealing a clean cavity. These cavities are then used to produce multiple identical wax models. Each wax piece is carefully assembled into a tree-like structure, which is placed into a metal flask. Liquid investment, a heat-resistant plaster is poured in, surrounding the wax. The investment is then allowed to cure completely, turning from fluid to solid stone. Next, it's time for burnout. The entire flask is placed in a kiln, where the wax vaporizes and exits, leaving behind a perfect mold. Molten gold or other metal is then poured into this space, recreating the original model in solid form. From a soft wax impression to gleaming gold, every step in this process is a blend of artistry and metallurgy. Steel doesn't bend easily, but this machine makes it look effortless. Let's take a closer look at this turnable section roller in action. Large steel profiles are loaded onto the rollers, which rotate with immense force. The turnable top roll allows different bending orientations, ideal for both rings and spirals. With each pass, the metal gradually curves, maintaining even pressure across the profile. You can almost feel the torque at work. Side supports guide the material, ensuring stability and accuracy. Adjustments can be made mid-process, offering both flexibility and control. From architectural frames to industrial rings, this machine handles tough materials with finesse. Its strength, precision, and clever design, all rolled into one. This is modern manufacturing, automated, efficient, and accurate down to the last detail. At EMC Group, up to 80% of machining and 70% of assembly is performed by automated lines. That's not just efficiency, it's consistency at scale. Robotic arms load and unload parts, guided by vision sensors. High-speed CNC machines cut, drill, and shape each component with minimal human intervention. Assembled parts are transferred through conveyor systems, where robotic modules fasten, seal, or test with precision. Each production stage is digitally visualized. Operators monitor quality and status in real time. The result? Reliable automation that ensures performance, reduces defects, and delivers speed. In a world where timing matters and tolerance is tight, this is next-level process control in action. Here, molten iron flows with purpose, every pore shaped by experience, every form built to endure. The process begins with molding. Sand molds are compacted and shaped to form negative impressions of the final part. These molds are aligned and closed, ready to receive liquid metal. Cast iron is melted in a furnace, reaching temperatures above 1,400 degrees Celsius. Once the correct temperature and composition are confirmed, the glowing metal is tapped and poured into the mold cavities. Timing is everything. Each second of the pour affects how well the iron fills the finest contours. As it cools, the iron solidifies into its final form. Molds are then broken apart, revealing rough castings that are sent for surface cleaning. Excess material is trimmed, and parts are inspected for integrity and defects. Deep inside the mill, steel slices through without heat. This is cold rolling at its finest. The process begins when massive steel coils are placed onto the decoiler. As the reel spins, the strip feeds into the rolling mill under precise tension. Unlike hot rolling, these powerful rollers compress the metal at room temperature. Each pass reduces thickness while enhancing surface smoothness, toughness, and structural integrity. The sound is unmistakable, a rhythmic hum of pressure and motion working in sync. You can almost feel the resistance in every roll as the steel is tamed into exacting dimensions. Operators monitor live metrics, adjusting for speed, tension, and thickness within millisecond intervals. Any deviation is flagged and corrected instantly. Quality is non-negotiable. Guided by real-time sensors, the strip stays perfectly aligned and uniformly tensioned. Every inch of the coil gets the same treatment. Once the desired specifications are reached, the strip exits the mill and winds neatly onto the recoiler, ready for its next journey. Whether it heads to stamping presses, coating lines, or machining centers, it's guaranteed to be consistent and reliable. Cold rolling isn't just reshaping metal, it's refining it. It's precision-engineered pressure that transforms raw steel into high-performance material with improved strength, surface finish, and exact dimensions. How is a kitchen knife crafted to perfection? Step into a Alvangan workshop and witness the transformation from raw steel to razor-sharp precision. It all begins with high-grade materials: chrome molybdenum vanadium alloy, Damascus VG10, or hardened high-carbon steel. Blanks are split-cut or forged, depending on the design, then punched and deburred to form the rough knife shape. After perforations are added, the blades enter the hardening phase, heated, oil-quenched, and straightened for durability. Next, the blades undergo grinding and drying, followed by pre-grinding the bolster. The handle scales are then carefully mounted by hand, a step where the grip and balance of the knife begin to take shape. After that, artisans perform detailed hand-finishing work on the handles, polishing every edge and curve until the fit and feel are flawless. The cutting edge is sharpened using traditional whetstone techniques in the final honing stage. Every blade is tested under inspection lights to ensure flawless geometry and alignment. Each knife passes through up to 45 steps, many done by hand, to ensure excellence. In the end, it's not just a knife. It's a tool shaped by skill, tradition, and relentless precision. Steam power still drives the future, quietly and efficiently. At this facility, precision-made turbines and boilers begin with machining the rotors and housings. These core components are assembled in large halls and tested under real operating conditions. From 2 to 70 megawatts, each unit is custom engineered to meet specific energy needs. It's not just about power. It's about reliability, sustainability, and decades of know-how built into every rotation. Want a smarter, faster way to build with light steel? Here's how Total Joist transforms floor framing. These steel joists arrive, pre-cut and labeled, no guesswork, no waste. Each piece includes service holes aligned across the run, making it easy for plumbing and electrical to pass through later. The layout begins with steel tracks mounted to wall studs, followed by lifting joists into place and securing connectors. Thanks to adjustable slots, minor site variations are no problem. Steel decking or sheathing is fastened on top, stabilizing the floor and preparing it for concrete topping. With a UL-rated fire resistance and moisture-proof design, offshore wind power starts far from land, and it all begins with precise coordination at sea. In this video, the Seajax Leviathan prepares for turbine installation at the Greater Gabbard offshore wind farm. First, the vessel navigates to the site and lowers its legs to the seabed, lifting itself above water for a stable working platform. Tower sections, blades, and nacelles are delivered by barge and lifted on board. Using its massive crane, the vessel hoists each tower segment and bolts them together mid-air. The nacelle, housing the generator, is then mounted, followed by the giant rotor blades. Each step is timed with tidal and wind conditions. Offshore construction demands grit, engineering precision, and absolute focus, one turbine at a time. What does it take to form massive steel plates into high-strength, large-diameter pipes? This Chinese facility, outfitted with SMS mirror technology, offers a powerful answer. It begins with giant flat steel plates, stacked and ready. They're first beveled along the edges to ensure a tight seam during welding. Each plate is then pre-bent, shaping the ends to begin the curve. Next, hydraulic rollers form the full cylindrical body. The plate passes through a 3-roll bending machine, gradually turning flat steel into a complete pipe shell. After bending, the open seam is tack-welded to lock the shape. The pipe is then rotated and clamped for precision submerged arc welding, delivering deep uniform welds along the seam. Multiple sensors monitor temperature and arc stability throughout the welding sequence. Once the shape is consistent, it's time to weld the inner seams first using automated systems, followed by the outer seams, ensuring a full penetration, high-strength bond. The pipe is then flipped and aligned again for ultrasonic and radiographic inspections. If any deviation is detected, advanced repair stations immediately address it before the pipe continues. Precision is key. Any defect means rework. That's why each weld zone is scanned, tested, and verified before moving forward. To maintain structural integrity, the pipe undergoes an expanding process, forcing an internal mandrel outward, which aligns the entire diameter uniformly. After that comes hydrostatic testing. High-pressure water is pumped inside the pipe to ensure it can withstand real-world loads. Finally, the exterior is coated for corrosion resistance, and the ends are beveled to match customer requirements. From flat plate to finished pipe, every step is engineered for performance, durability, and scale. These pipes are built to transport oil, gas, or water across countries, and every weld carries that responsibility. Efficient scrap processing is the heart of modern steel recycling. The journey starts as scrap metal is sorted and cleaned, then loaded into powerful shredders that break it down for further use. Compressed scrap is then delivered by bucket systems or vibro feeders, streamlining handling and keeping production steady. Watching piles of metal quickly transformed and organized for the next stage is pretty exciting. This streamlined process not only saves energy but also shortens processing cycles. Every step shows how smart recycling makes steel production faster and more sustainable. Every tough trailer starts its life here, where steel beams are laid out and locked into position. Skilled welders fuse each joint and add reinforcing plates for extra durability. Automated systems guarantee clean, consistent welds all along the frame. Watching sparks fly as the chassis takes shape is always a thrill. In the end, it's all about strength built for the open road. The production of a carbon steel overpack for high-level radioactive waste storage is an impressive display of engineering and control. It all starts with carbon steel, heated to a scorching 1,000 degrees Celsius inside a massive furnace. At this stage, the softened steel is shaped into a thick-walled cylinder, preparing it for the powerful pressing process. A 2,000-ton press then applies tremendous force, shaping the body while ensuring an even thickness throughout. You can almost feel the power behind every press. The next steps involve carefully adjusting the cylinder's edges and performing both internal and external surface treatments. Precision at this stage is crucial, as any flaw could compromise the safety of the final product. The interior and exterior are inspected for any defects, using advanced measurement tools to guarantee perfect quality. Meanwhile, the lid is processed separately, machined to exact dimensions to match the main body. When both parts are ready, they are joined together using TIG welding, a process that demands skill and concentration. The weld penetrates 19 centimeters deep, with the container rotated steadily at 6 to 10 centimeters per minute, ensuring even fusion at every point. Final welding is performed just 2 centimeters from the surface, sealing the overpack completely. Seeing each of these heavy-duty operations up close highlights the careful balance between brute force and precision. It's a fascinating process that plays a critical role in safely managing radioactive waste for generations. Few things are more impressive than the making of a steel wheel built for heavy trucks. It starts with thick steel discs, stamped and cut to size, then shaped by hydraulic presses into the rough wheel form. Giant tools mold the center hub and outer rim in a single powerful motion. Flash trimming ensures each wheel is perfectly round, and high-speed drills create bolt holes with pinpoint accuracy. Each wheel undergoes strict inspections for strength and balance. Next, hydraulic presses perform final shaping, forming the wheel profile with extreme force. The wheels then move to shot blasting, where steel beads clean and smooth every surface. The final step. Wheels are sprayed with a protective finish, leaving each rim gleaming and ready for the toughest jobs on the road.
The Super Tyro screw flight forming machine is designed to form sectional screw flights with high precision and consistency, regardless of operator experience. It excels in creating screw flights where the pitch is larger than the outside diameter, a challenging task with traditional methods. Using this latest technology, the Super Tyro can form these flights in under 60 seconds, with perfect matching ends and identical helix forms, whether left hand or right hand. The machine ensures precise and consistent results, eliminating the need for an experienced operator, which would otherwise take over 5 minutes to achieve manually, often without guaranteed accuracy. This spiral helix blade machine is used to form continuous helical blades for augers or screw conveyors. The process begins by feeding flat steel or other materials into the machine, where it is cut into strips. These strips are then shaped into a helical form through a series of rollers and dies that apply precise pressure. The machine adjusts the pitch and diameter of the blade to meet the required specifications. It ensures uniformity and accuracy by maintaining consistent speed and force during the shaping process. The resulting helix blades are commonly used in industries like agriculture, mining, and material handling, where they are vital for conveying and mixing materials. U-shaped steel is a versatile product widely used in construction, manufacturing, and infrastructure projects. The production of U-shaped steel involves transforming steel billets into the desired cross-sectional shape through a hot rolling process. The billets used for U-shaped steel production in hot rolling mills have a high degree of cleanliness, consistency, and uniform chemical composition. Before the steel billets can be processed, they must be heated to a temperature suitable for hot rolling. This typically involves raising the temperature of the billets to 1,100 to 1,300 degrees Celsius in a reheating furnace. Heating the billets to such high temperatures makes the steel more malleable, facilitating deformation and the rolling process. The reheating furnace used in FICO's mill in Iran is designed to ensure uniform heating across the billets, thus preventing temperature gradients that could cause mechanical inconsistencies during the rolling process. Once the billets are uniformly heated, they move on to the first stage of the rolling process, known as the breakdown stage. FICO's medium-section mill employs a two-high shiftable breakdown housingless mill stand for this operation. The purpose of this initial rolling step is to reduce the billet's cross-sectional dimensions and elongate it into a bar, preparing it for further rolling and shaping. The two-high shiftable stand offers flexibility in adjusting the rolls for different cross-sections and ensures that the steel passes through the mill with precision. This housingless design allows for greater control over roll separation forces and the material flow during the rolling process. During this breakdown stage, the steel bar begins to take on a more refined, elongated form, setting the stage for subsequent rolling. Intermediate rolling, universal and 2-high mill stands. Following the breakdown process, the elongated steel bar enters the intermediate rolling stage, which involves passing through 10 continuous universal and 2-high mill stands. These stands are equipped with pairs of horizontal and vertical rolls that work together to reduce the cross-sectional dimensions of the bar even further. The universal mill stands are particularly useful for producing U-shaped sections because they allow precise control over the width and height of the section simultaneously. The horizontal rolls control the flange width, the outer parts of the U-shape, while the vertical rolls adjust the web height, the central part of the U-section. This capability of universal stands to shape the material in multiple directions during one pass makes them ideal for forming complex profiles such as U-channels. Meanwhile, the 2-high mill stands provide additional rolling stages, focusing on reducing the thickness and elongating the steel bar. The combination of universal and 2-high stands ensures the U-channel receives its precise, final shape with tight dimensional tolerances. After passing through the universal and 2-high stands, the U-shaped steel enters the finishing stage. At this point, the cross-sectional dimensions are mostly correct, but the product may have minor imperfections or residual curvature from the rolling process. To address this, a multi-pitch straightener is employed. The multi-pitch straightener is a set of rolls designed to remove any bending or warping from the steel that may have occurred during earlier rolling stages. By applying corrective forces, the straightener ensures that the final U-shaped steel has straight, uniform edges and the desired U profile. After straightening, the hot U-shaped steel is cooled on a cooling bed. The state-of-the-art medium section mill installed by FACO in Iran comes with several advantages. First, the 2-high shiftable breakdown housingless mill stand provides significant flexibility, allowing for quick adjustments and reduced downtime during production. The 10 continuous universal and 2-high mill stands ensure precision in forming the U-channel profile, delivering uniformity across each section produced. Additionally, the inclusion of a multi-pitch straightener and magnetic stacking system reflects the emphasis on quality control and efficiency. The straightener ensures a flawless final product, while the magnetic stacking system speeds up the packaging process and minimizes handling damage. Quality control experts check the product's height, flange width, web thickness, and overall straightness, ensuring that each section meets customer specifications and relevant industry standards. After the U-shaped steel sections have passed inspection, they are automatically stacked using a magnetic stacking system. This technology allows for efficient, hands-free handling of the steel sections, minimizing the risk of damage and enhancing the speed of the packaging process. The magnetic system ensures that the U-channels are neatly and securely arranged into bundles, which are then tied together and prepared for shipment. This manufacturing process takes place in sophisticated facilities equipped with modern machinery, such as a state-of-the-art medium-section mill. In Iran, FACO has installed one such advanced rolling mill system, consisting of various specialized components, including a 2-high shiftable breakdown housingless mill stand, 10 continuous universal 2-high mill stands, a multi-pitch straightener, and a magnetic stacking system.
It's incredible to see a block of aluminum precisely machined into a complex blower wheel using advanced CNC milling. The process starts with Z-level roughing, where a 6mm flat end mill cuts away large amounts of material in 0.8mm deep passes and a 4.8mm step over, advancing at 32mm per second. The tool carves out the main shape, leaving a rough outline that already hints at the final form. Next, the machine switches to circle spiral finishing with a 6mm ball and mill. Here, the tool follows a 3-axis simultaneous tool path, moving at a tight 0.07mm step over and 35mm per second feed rate. Every detail, curves, surfaces, and pockets is refined in a series of smooth, coordinated moves. Watching the mill glide through aluminum, transforming blocky raw material into intricate aerodynamic blades, is genuinely satisfying for any manufacturing enthusiast. The result is a perfectly contoured blower wheel, ready for high-speed use. Seeing this level of precision and efficiency up close really makes you appreciate the engineering behind modern CNC machining. The finished surface looks flawless under the light, with every contour perfectly defined. Each step highlights the power and finesse of CNC technology. Step inside a UK sand casting foundry, where molten metal meets precision engineering. The process starts with skilled workers packing sand tightly around a pattern to form a mold. Once the mold is ready, molten non-ferrous metal is poured in, filling every detail. After cooling, the sand is broken away to reveal the raw casting. Each part is then carefully cleaned, with excess material trimmed off. The castings move on to CNC machining, where tight tolerances are achieved for aerospace, marine, and automotive uses. Final inspection ensures every piece meets strict quality standards. Watching this teamwork and attention to detail in action is truly impressive. These castings are built to perform in the toughest industries. Watching skilled technicians overhaul industrial gas turbines is a real feat of engineering. Each turbine arrives for a full teardown, with components carefully inspected and cleaned. Damaged parts are repaired or replaced, and every module is rebuilt to exact specs. Advanced diagnostic tools ensure everything meets tight tolerances. The process wraps up with thorough testing before the turbine is cleared for high-demand operation. The precision and teamwork on display here are seriously impressive. Structural steel fabrication at this level is seriously impressive. The process begins with precise computer-aided design, transforming architectural plans into machine-ready models. Massive steel plates and beams are delivered and quickly sorted for each project. Automated roll-forming machines bend and cut the steel with tight tolerances, producing beams, columns, and custom shapes needed for large structures. Watching the raw steel glide through rollers, then emerge perfectly shaped, never gets old. Once shaped, the steel parts move to the robotic welding stations. Here, synchronized robots handle the heavy lifting, positioning, clamping, and welding each piece according to the 3D models. The precision is remarkable, with every seam placed exactly where it belongs. Each weld is automatically checked, and any deviation triggers immediate correction. After this initial welding, the components go through cutting and punching stations, where holes and slots are created with high-speed presses and CNC cutters. Secondary welding follows to join any additional parts and reinforce structural connections. Then, protective coatings are applied to ensure long-term durability. The finished elements are loaded and shipped to construction sites, ready for rapid assembly. The scale and efficiency on display here makes structural steel fabrication feel like a true art form. Seeing these huge frames built with such accuracy and speed is an amazing testament to what modern engineering can accomplish. Steel forging doesn't get more intense than this. The process begins by heating a billet until it glows. Using tongs, operators place it between closed dies. With a powerful press, the metal is first formed into a cylinder, then punched through the center while still blazing hot. Next, the axial closed die rolling machine takes over, expanding the billet outward and rolling it into a precise ring shape. Finally, a massive press flattens and finishes the red-hot ring, ensuring the perfect profile and thickness. Each pass controls thickness and diameter with remarkable accuracy. It's incredible to see raw materials shaped into heavy-duty rings used in industries where strength is everything. Get ready to see steel transformed into essential tools. The journey begins with metal billets, heated in an electric furnace until they glow white-hot. Workers position each billet on a die, and a powerful press shapes it into the jaws of pliers with several massive strikes. Another press trims away excess steel, giving each half its exact outline. For gripping power, a milling machine carves sharp, precise teeth into the jaws under a stream of cooling fluid. Heat treatment is next. Halves are baked at over 800 degrees Celsius for 2 hours, then rapidly cooled in a salt bath for maximum hardness. Some jaws are even laser hardened for extra durability. The halves are then assembled using a steel pin, secured by high-speed friction or press fitting, depending on the type. Edges are ground perfectly flat with abrasive wheels, and another round of heat treatment in oil ensures lasting strength. A protective anti-corrosion bath keeps the metal rust-free, and robotic arms polish each surface to a smooth finish. The company's logo and product number are laser-etched onto the steel. Finally, handles are dipped in liquid vinyl, then baked so the coating cures into a soft, comfortable grip. It's amazing to watch every step turn raw steel into reliable pliers, ready for any job. The multi-process vertical mill turning machine is a true powerhouse at precision manufacturing. Everything starts with massive workpieces being securely clamped onto the vertical table. The setup alone is impressive. Heavy steel components, precisely aligned, ready for a series of advanced machining operations. First, vertical turning operations begin as the table rotates, and a robust cutting tool shapes the outer diameter, bringing rough parts to the required roundness and size. The sheer stability of the vertical axis keeps vibrations low, even with the toughest materials. Next comes milling, with the head moving in multiple axes to create features like slots, holes, and pockets directly on the same setup. It's remarkable to see the tool change systems in action, automatically swapping out cutters for different jobs without stopping the process. The machine's ability to combine multiple operations in a single setup saves enormous time and reduces error. You can almost feel the power with every cut, as raw steel is transformed right before your eyes. Drilling cycles follow, and the machine's flexibility becomes clear, switching between roughing and finishing, changing tools and cutting directions, all controlled by advanced CNC programming. Complex contours and intricate surfaces are carved with precision, thanks to multi-axis simultaneous movement. The coolant system keeps temperatures in check, and every pass leaves the workpiece closer to its final, flawless shape. Once machining is complete, parts are measured for accuracy, with digital probes ensuring tolerances are met. The efficiency is hard to ignore. Reduced setup times, fewer reclampings, and perfect integration between turning, milling, and drilling. Watching this technology in action, it's easy to see why vertical mill turn centers are at the core of high-value, high-precision manufacturing. The engineering and smooth workflow are simply captivating. Spiral bevel gear production with a 5-axis machining center is a masterclass in precision. The process begins as a solid blank is mounted on the DMU 201. Rough machining shapes the gear's distinctive spiral teeth, with each axis moving in perfect harmony to carve the complex geometry. You can almost feel the power and accuracy as the cutter glides across the metal. This level of control ensures every tooth meets tight engineering standards. Watching the gear come to life is seriously satisfying for anyone who loves manufacturing. Cold forging begins with steel rods pressed into precise forms for tie rods and ball pens. Automated machines then roll threads and grooves, ensuring perfect fit and strength. Every part is inspected by high-tech sensors, guaranteeing strict quality standards. It's impressive to see raw steel transformed with such force and control. These components play a crucial role in steering and engine systems every day.